Welcome to this explainer on Grade 7 Science Essentials. Now, before you groan and think we're just taking a boring trip back to middle school, hear me out. I want you to look at this through a totally different lens. Science, it isn't just a subject you're forced to take, it's a map. It's literally a map of the universe, and today we're going to learn exactly how to read it.
You know, if science has ever felt difficult or overwhelming to you, I promise it is not a lack of ability. It's just that relying on memorizing isolated terms, well, it's eventually going to fail you. We've all been there, right? Staring at a massive list of words like mitochondria and refraction, just crossing our fingers and hoping they stick. But science isn't a subject where you just memorize facts and hope for the best. Not at all. It's about observing things, looking for patterns, testing ideas, and explaining the why behind it all. When it comes down to it, science is pure organization.
Think about your own mind like a desk for a second. A messy desk makes even the simplest task feel incredibly stressful, right? But a well-organized desk, that helps you actually see what to do next. When terms, experiments, graphs, and calculations are all just thrown together in a pile, every single question feels impossible. But once you learn how to sort them out, the entire universe suddenly becomes so much easier to handle.
So here's our game plan. We're going to use Grade 7 Science as our ultimate desk organizer. First, organizing the messy desk. Second, the rules of life. Third, making sense of matter. Fourth, waves, light, and sound. And finally, number 5, the power of mistakes.
Let's jump right in. Section 1, organizing the messy desk.
Okay, so we really need to nail down the difference between two foundational tools, observation and experiment. Observation is simply noticing and recording facts as they already are. Like watching a plant naturally bend toward the window, that's an observation. You aren't changing a thing. But an experiment, now that is active. You're testing an idea by intentionally changing one single condition. Think giving one plant water and totally depriving another plant of water, just to test a hypothesis. The golden rule here, and this is absolutely crucial, you can only change one condition at a time. If you change a bunch of things at once, you'll literally never know what actually caused a result.
Moving right along to Section 2, the rules of life.
Biology can seem incredibly chaotic, right? But instead of getting overwhelmed by the sheer, crazy variety of plants, animals, and microscopic bugs out there, we can map all of life using a few shared survival functions. A dog running, a mushroom sprouting in your yard, a tiny single-celled organism, they all check these exact same boxes. They take in nutrition, they get rid of waste, they grow, reproduce, and respond to stimuli. Oh, and respiration. Now, this is probably one of the most misunderstood functions on the list. People usually think respiration just means breathing air into your lungs. Actually, scratch that, it's way more fundamental. It's the chemical process of releasing energy from nutrients, which means, yes, even plants respire, day and night, just like you and me.
And that brings us to a classic mix-up, but it's honestly fascinating once you sort it out. Plants are just incredible because they do both photosynthesis and respiration, but for entirely opposite reasons. Photosynthesis is a plant using light energy to make and store food. Makes sense, right? And it only happens when the sun is out. But respiration? That's the plant actively breaking down that stored food to release energy so it can actually live, grow, and do its thing. And since the plant needs energy to survive all the time, respiration is happening 24/7 around the clock. Think of it like a phone battery. Photosynthesis charges the battery, and respiration drains it to actually power the plant.
All right, let's shift gears. Section 3, making sense of matter.
When we zoom in on chemistry, the particle model perfectly organizes our scattered facts about matter. It's all about how closely packed and how active those invisible particles are. In a solid, particles are locked together tightly, just kind of vibrating in place, which is exactly why a rock holds its shape. Now add some heat energy to the mix, and they start sliding past each other. Boom! Now you have a liquid that flows. Add even more energy, and they break apart entirely, zooming around frantically as a gas. It's the exact same stuff, like ice, water, and steam, just moving with different levels of energy. So why does a tiny metal coin sink to the bottom of a pool, but a massive, heavy log floats on top? Well, it isn't about overall weight at all. It is strictly about density. Density is just how much stuff, how much mass, is packed into a specific amount of space. A tiny coin has its mass packed incredibly tight. That gives it a really high density, higher than water, so it sinks right to the bottom. But a giant log, its mass is spread way out, creating a lower density than the water, so it floats. Basically, density answers one simple question: how crowded are the particles in that specific space?
Okay, let's pose a little problem-solving challenge. If you have muddy water, a standard paper filter catches the big dirt particles easily. But what if you have salt water?
The salt is completely dissolved. The particles are way too small and will pass right through the filter paper like it's not even there. So, what's the logical next step if we desperately need to collect that pure drinking water? We have to look at the different physical properties of the salt in the water to find our loophole.
And that loophole is boiling points. This process is called distillation. Because water boils at a much, much lower temperature than salt, we just add heat. The water turns into a vapor and escapes, leaving the solid salt trapped behind. But wait, remember our goal? We want the water, right? So we have to catch that escaping vapor in a tube, cool it down, and let it condense back into pure liquid water in a totally separate container. It's a completely elegant solution based purely on knowing how matter behaves.
So nature essentially gives us two paths here, and your choice depends entirely on your end goal. You have to ask yourself, do you want the salt or do you want the water? If you just want the salt, you use evaporation. You just heat the mixture, let the water vanish into the air, and scrape up the salt that's left behind. Easy. But if you want to drink that water, you absolutely must use distillation to trap, cool, and condense the vapor. The method you choose always boils down, pun intended, to the property of the substance and what exactly you're trying to collect.
Which brings us to Section 4, Waves, Light, and Sound. Both light and sound are simply ways that energy travels from one place to another. But there is a massive, fundamental difference in how they pull it off. Light can cross the completely empty vacuum of space to reach Earth from the sun. It literally doesn't need anything to travel through. Sound, on the other hand, is what we call a mechanical wave. It completely, 100% relies on vibrating particles physically bumping into each other. Without a medium like air, water, or the solid ground, sound simply cannot exist, and that is exactly why, in the deep vacuum of space, it is completely and utterly silent.
Let's take a second to untangle two traits of sound that get mixed up constantly: loudness and pitch. Loudness is all about the size of the vibration, what scientists call amplitude. If you smash a drum with a ton of force, you create a massive vibration and you get a really loud sound. But pitch is about how fast those vibrations are happening, the frequency. A tiny quiet whistle might have a super small amplitude, so it's not loud at all, but it vibrates incredibly fast, giving it a piercingly high pitch. So just remember, bigger vibration equals louder sound. Faster vibration equals higher pitch.
Finally, we arrive at Section 5, the power of mistakes.
Let's be real for a second. In the actual world, experiments go wrong all the time. Filter paper tears, water boils over, light rays get measured wrong. It happens. But instead of just marking an answer wrong and moving on, science forces us to stop and ask this incredibly powerful question: why did it fail? By doing this, we turn a total failure into a vital piece of data. Identifying your error isn't about making excuses, it's actually about improving the scientific reliability of everything you do next.
This basic process is literally the scientific method acting in your daily life. Here is how you systematically solve a failure. First, the error. What exactly went wrong? Well, maybe the filtered water was still muddy. Second, the cause. Why did it happen? Oh, the filter paper tore. Third, the effect. How did that alter the result? Mud particles passed right through the tear into our clean beaker. And finally, the improvement. How do we fix it for next time? Maybe we pour the liquid much slower, down a glass rod, so the paper doesn't rip. See what happened there? You just took chaos and turned it into an organized, improved system.
To wrap up this explainer, I want you to remember that organizing your own mental, messy desk isn't about memorizing the universe perfectly. No one can do that. It's about giving yourself the tools to constantly ask better questions. Whether you're looking at a houseplant on your windowsill, a glass of ice water, or listening to the sound of a passing car, you now have the map to understand the fundamental rules they follow. So I'm going to leave you with this thought. Knowing what you know right now about observation, evidence, and asking the right questions, if you could ask one better question today about the physical world around you, what would it be?